Hardesty from Ithaca, New York. He has provided some of the cover photos for two issues of Extraordinary Science. The pretty cover with the tubes and the plants in them, and also the violet ray cover. He builds and sells equipment of the Tesla type nature up there in Ithaca, and he does a lot of other things. He's spoken here for the symposium before, and he wants us to let his talk speak for itself. He's going to be talking about a Norwegian physicist who's most known for his work on the Aurora Borealis, and his talk is entitled Experiments of Kristian Birkeland. Jim Hardesty.
Good morning, and I'm very happy to be here. Is this working? Everyone can hear me, I hope? Good.
Talk louder.
Talk louder. Okay, all righty. Before I start, just a couple of things I'd like to say. First of all, I always like to mention a friend of many of us, Harry Goldman, who is not with us here today. He's busy and not feeling well. A lot of you, I hope, know Harry as the founder and person that's kept the Tesla Coil Builder Society alive for many years. And we keep trying to get him to come out here every year, but I'd like to at least acknowledge him because he's certainly been a great deal of help and inspiration to all of us. He's gone in the hospital on the 6th of August, I believe, for an operation, and anybody who, I'm sure, drop him a line or whatever and wish him well, it would be appreciated, I'm positive. The talk this morning is about the Norwegian physicist Kristian Birkeland, who lived from 1867 to 1917. The reason why I've picked this particular topic to talk about here is that my contributions, I hope they are that, to the knowledge that's put forward here has been in the area of vacuum discharge tubes and in the work of physicists in the latter part of the 19th and early 20th century dealing with the discovery of the electron and some of the incredible things that have come from that. And I feel it ties together with the work that Nikola Tesla is involved with because of his own work with vacuum tubes, which I think most of the information and discoveries on that is yet to come. I hope that the presentation here, which I'm going to try and keep very simple because there's so darn many things to talk about, will be of some inspiration, at least some points of departure for other researchers and so on, perhaps in the opening up of some of these wonderful mysteries concerning the electron and such. Birkeland is a rather curious figure, and he is well known for a number of things besides his vacuum discharge studies in relationship to the aurora. In around 1890, he was finishing up his studies under Henry Poincaré. He also spent time studying electromagnetic topics with people such as Hertz, as well as another gentleman, which we won't talk about, Delarive. So his pedigree is pretty good. He, in my opinion, should be considered as one of the Maxwellians, I think they call them, such as Heaviside and Fitzgerald and so on, who, Maxwell's theories were really not, I might say, modified reasonably so that they had applications until a number of these people really did some experiments and really made it more understandable and workable. Birkeland, they said from the time he was a child, I guess this is said of a lot of people, people play with different things. They said that from the time he was able to do anything, he always had a magnet in his hand, dealing with magnets and so on, and so it is not untrue in his later life that should be one of the important things that he worked on. He is also famous for early, I guess you might call them railgun experiments with electromagnetic cannons. He was able to did some amazing experiments. I won't go into that. The only funny story is that he had built this amazing cannon, a magnetic cannon, which worked very well until he had the I guess the military and the financiers up there when he operated it, and It was a grand display, he said, but his stock went from 300 down to 0 because everything went up in flames. However, the projectile that he had set in there hit the target some considerable distance away, but it didn't quite work out. He also was one of the first, in fact, the first person in Norway after the discovery of X-rays to immediately begin to demonstrate X-rays and to have tubes and equipment made to run experiments with cathode rays and X-rays. And of course, the fact that magnetism was his great interest, he experimented with deflection of cathode rays in a magnetic field, which leads on to where we're going to be going with this talk about his work with the aurora. And he also spent a great deal of time and energy setting up observatories in the polar region in northern Norway as well to observe and study the effect of what he called magnetic storms occurring as in conjunction with auroral phenomena, so that he could actually make magnetic measurements, and he could also get some idea about field strengths and so on that were going on. So he had a considerable amount of information on that, which was published in his greatest work, huge book that's not readily available, but I did manage to get a copy of it to study from the Cornell University Library. It's called On the Cause of Magnetic Storms, and Study of the Aurora Polaris Expedition of 1902 and 1903, in which he and a group of people set up observatories at the best of which were at Mount Haldey in northern Norway. And they spent a lot of time running and doing experiments of that particular nature. I can see forward here. Maybe all I need to do is see my crib sheet here. If you could maybe turn the lights down a little bit, Daryl. Just let me have this here, then we can see the slides a little bit better. And I think that's pretty good. That slide there looks like it had a little bit of difficulty. Anyway, this is his major out on top of Mount Hadle in northern Norway, his aurora and magnetic storm observation area. Another thing which occurred, which I think is very curious here, this is a model. Can you hear me? Is this working okay? Okay, yeah, it's, huh? Little loud, boy. In the early part of the 20th century at the university in Oslo, Birkeland's early works and with the cause of the aurora and the... I'm jumping a little bit ahead here, but I want to show you this just so we get some ideas. This is a actual wires, and it was built by a physicist there by the name of Carl Sturmer. And Sturmer, having looked at a lot of Birkeland's ideas about the quantum particles coming from the sun and getting into the magnetic field of the Earth and coming down into that magnetic field and causing excitation of oxygen and nitrogen in the atmosphere, and then creating auroral displays. He had postulated this in the 1890s. This is models, and there are a number of them built here. This is another one. Sturmer designed these things and mathematically calculated in conjunction with Poincaré to try to give an idea about what happens if you were to get, let's see, in the late 1890s, I think they were still calling them corpuscles, but electrons coming from the sun, and then in what we call the solar wind, getting into the atmosphere of the Earth and creating, seeing what kind of trajectories, I believe the word they use, would happen here. This is another example of it, and we'll just move on. Here's another one, a very curious study made here. That's Carl Sturmer. And around 1902, his work was being done on this for anyone who has particular interest to study that. Now, we go to the next phase of things here, and I hope that some of the things I'm going to say this morning will also help us to have a little understanding of another presentation that my friend Jim Cruiser and I will be giving this afternoon at 3 o'clock, which is an actual demonstration of a classical vacuum discharge tubes, which were manufactured in the latter part of the 19th and a little bit in the early 20th century, including Crookes paddle wheel tubes and such. Will be quite a demonstration with a little bit of explanation here that might lend to a little clearer view of what we're going to be doing then. That's at 3 o'clock, by the way, and I hope you can attend that. That should be something very special. This particular thing here merely is looking at glow discharge, and these are a bunch of phenomena that are seen in glow discharge, that is pumping the air out of a tube and then introducing a DC high voltage at either end and creating different sorts of striations and dark spaces and so on like this. I have to have a few of these in here because one of the things that I want to explain is that people like Birkeland and Davik and the workers that were with them really at that particular time, and this is not only true of them, but when you think about people as far back as Faraday, Geisler, Hittorf, Crookes, Goldstein, Perrin, all these people who worked in this particular field, and some of you out in the audience who I know well, who we spent time dealing with this, know that there is a certain amazing, romantic, if you will, attractiveness to these kind of tubes. And so I just want to show a few and some effects. This is an extremely rare tube. It is a high-frequency X-ray tube that was actually manufactured about 1897. It's in the collection of the Antique Wireless Association in East Bloomfield in New York. And what you're seeing here is one side of an operation, and there's a hemisphere there that's made of German glass. So the electron impact, not the X-ray impact, the electron impact that's just bouncing off of the target that's in the center, will give you that apple green glow on the glass that's there. And these kind of observations at this point and a lot earlier, looking at other discharge tubes, really led people, especially Birkeland, to give consideration to the origin of the aurora borealis in terms of the same effect that was going on here. And here is the same tube again. It's running in opposite polarity this time, so that the center terminals, the cathodes, you get a different kind of effect. You can see the target in the center there. Just moving along through some of these. This is another interesting colors available here. This is a gas X-ray tube manufactured about 1906. This here is the anode. This is the cathode over here. You can see a little bit of ion impact glow here. This tube actually is in operation, and you can see the cathode beam. This is a stream of electrons traveling across here and hitting the target here, and you can barely see down here. There's a regular glass window. This tube is made of lead glass before the X-rays can come on here. It's just kind of a safety tube, but you can see the focused cathode beam striking the target. And the colors associated with that. Here's a little more of that. This is the opposite polarity. Again, you can see it's running in the opposite way. That is, this is the target here. It's a tungsten button inside a copper, and there's the cathode back there. And I'm just showing you some of the colors. That's not a really great shot of the same thing we looked at before. And this is a little harder to see because the lights are still on, but you can actually see here the electron impact that's hitting the target, and there's a certain fluorescence occurring in there that really is where the X-rays are being produced. There is a kind of a very colorful display. All of these things were viewed by Birkeland and other scientists at the time. Birkeland himself decided that this was a study that really could lead to some understandings of what the auroral phenomenon were about. And of course, living in Norway, he saw that all the time, and the curiosity about this, plus the magnetic effects and all this, led him to begin his particular experiments here. I just show here a couple. These are more of some of the vacuum discharge tubes that people like Birkeland and others were looking at. As some rather phenomenal effects here of electron bombardment and fluorescence, as in here you can see that this is the cathode here. Electron beam strikes these objects down here. I don't know exactly what that is. And causing them to fluoresce. That was very common. A lot of studies going on in the 1890s in this. These tubes will be demonstrated this afternoon. You can see these up close. This is the star of the show, a Geisler tube type where there's different colored liquids and so on in here for light refraction coming through these different glass, and there are different types of glass in here. Just stop a moment to observe the marvelous craftsmanship and appreciation of the Victorian craftsman in blowing something like this out of glass just for the sheer pleasure of observing electrons at work. I think it's commendable. Something today we might get some things from. And this is the same kind of thing of bombarding. This was on the front cover of the Extraordinary Science magazine. That's another bombardment tube. We have a surprise for you this afternoon. We have a tube that I feel that is orders of magnitude beyond the beauty of this tube, but we'll let you see that this afternoon for real. And quickly here, this is a vacuum discharge tube, and I'll just quickly run by this. What we're doing here is the same thing as a spark discharge in the atmosphere. Essentially, you turn on an induction coil and the spark jumping between the leads of the induction coil. It's about the same thing that's happening here, except that the mean free path of the electrons at atmospheric pressure does not allow them to travel very far before they have a lot of inelastic collisions with atoms of oxygen and nitrogen and so on, so that the spark is a lot shorter. If you begin to pump the tube down, then the discharge can become much longer, because the mean free path, that is the path that the electron can travel from the cathode to the anode, is considerably longer before all those electrons are used up in these inelastic collisions and the tube doesn't work. That's why even with high voltage you can see these corona discharges as this effect reaching out, ionizing the air and so on, trying to move forward. But I'm going to go through quickly what Birkeland and other scientists at the time actually were looking at. This here had been observed at these vacuums for centuries. I had said in my earlier paper 2 years ago that the first time this ever was observed was in 1674. A gentleman by the name of Picard at the Paris Observatory was walking around the barometer and was shaking this barometer, and the mercury sloshing around the tube actually was the phenomenon called triboluminescence, in which the mercury actually rubs electrons off the glass, and then there is a relaxation, recombination thing going on, and you see light actually. And he observed this and didn't really know what it was, but that was the first neon sign sort of thing, and after that there were many experiments. Let's take a look at it as we go through this a little further. This is a little brighter, and you can see there are certain effects here. I won't get into extremely detailed explanation of this, but the cathode is down at this end, and essentially what happens is normally gas that is unaffected, we wouldn't be able to conduct electricity, but due to cosmic rays and ultraviolet rays and other things, it can actually impact those atoms, ionize them, so we have positive ions and free electrons floating around in a tube like that. We can actually get those to be attracted to the poles of opposite to their own charge, and as electrons starting out from the cathode down here moving forward gain enough speed, the first thing they do is they gain enough speed to excite the oxygen and nitrogen atoms in the tube, and we'll get it moving a little faster, and then they can ionize. And the ionization process essentially produces enough free electrons that can, or free positive ions that can bombard the cathode and release more electrons and produce simply what's called a steady state in the glow discharge, which allows the thing to continue. Otherwise, those free particles would be used up and you wouldn't see a discharge anymore. But this produces a steady state, and as the electrons continue, their speed slows down. Essentially, in the discharge here, where you see there's a dark space there, it's called the Faraday dark space because Michael Faraday being the first person to observe it. Here we are again as the vacuum continues. We're at about 5 torr at the present time, and you begin to see another dark space appearing down here, which is called the Crookes dark space. Now we can see the Crookes dark space down by the cathode. Let me get this marvelous pointer here. The Crookes dark space is being shown here. Here's the Faraday dark space. So in other words, electrons have accelerated to the point where they can excite in the lighter parts, ionize as it gets darker, and then it really gets dark in here as they slow down. And then they accelerate in the field again and begin to excite again. And you will see, I believe, as we go along, there'll be something called the positive column here, which is, let's get to that. Some striations in this, barely see that. There we go. And those striations are basically kind of a speed observation of how fast those electrons are traveling, that they either excite or ionize. Ionization, recombination reactions produce a lot less light, fewer light photons, and do the exciting and relaxing experiences. Vacuum technologies in the, let me get a good shot of that here. Go back a little bit. The vacuum, level of vacuum could be told by measuring the Crookes dark space, which you can see down in here. And the larger the dark space, Crookes dark space appears at about 1/10 of a torr and begins to fill the entire tube as the vacuum continues. You could measure that, and early vacuum technology was set up so that you could measure it that way. Just looking, okay, so now armed with this knowledge, Birkeland observing beautiful auroral displays. And you can see various types here, arc and ribbon displays. The green color here is, see what I have written here. That's a lower altitude, I guess, response somewhere about 557 nanometers. That color we have, I'll just go through these quickly. They're just interesting effects. The colors, that's not that good. Yes, there's a good one. Only once in my life when I lived in Philadelphia when I was a kid did I ever see such a tremendous display in the sky that was totally fantastic of all these colors, such as you see here. Birkeland's observations of this led him to try to understand exactly what, that's a nice one there too, exactly what is going on with this. Essentially, there are a number of colors and their frequency ranges. They'll be in the paper you can just look at here. Essentially, electrons that are penetrating the atmosphere, moving a little bit ahead here, but at the penetration at 1 kilo electron volts is about to 150 to 200 kilometers. If they get up to 10 kilo electron volts, it's a penetration to about 100 kilometers, and then above 20 up to 30 keV, you can get down into the 90 kilometer range. Protons are a little bit different. They need a lot higher amount of energy to penetrate down into the atmosphere. Normally the dominant color that you see from atomic oxygen in these displays here, there's a beautiful one. Those are mostly red. That's is a green colored, about 557 nanometers. That's for atomic oxygen. Okay, a quick explanation of what's going on here, and Birkeland actually hit the nail right on the head with this, at least in his explanation of things. The sun, being a sort of a marvelous source of quantum particles, starting, I guess, somewhere in about the 1870s, a fellow by the name of Maunder had realized that there was a correlation between sunspots and auroral phenomenon, because he had made a statistical study of the whole operation and found out that there was, I believe it was something called the Maunder minimum in the 18th century, and where there were, for some 15 or 17 years, there was no auroral display at all. And up in the northern regions where that's very common, people began to wonder why, and that was documented. And so there was he theorized that the sunspots are actually some kind of magnetic windows in the sun's chromosphere, that which out of that very excited particles could be spewed out, and then the sun itself, having a tremendous interplanetary magnetic field, could actually send those particles throughout the solar system, and when they would get near a planet, that there were certain effects taking place. And basically, Jim Cora mentioned this morning, which I think was important, talking about you made it a mark about the aurora, is as time goes on, there's about 20 theories, and back in these days there was one really theory that Birkeland had, and a few other people, but the theories, and there's a lot of information. The more satellites that go up and the more information that's available, there's a lot of opinions about how it works, and I really don't want to spend time talking about that, although this particular one doesn't look too bad. The interplanetary magnetic field brings electrons and protons from the nuclear reactions on the sun down, and when they get near the Earth's magnetic field, or the magnetosphere, there's a specific effect that produces the, I think it's called the magnetotail, which is on the opposite side from the sun, out and back of the Earth, and down in there, when the particles from the sun's own transmission of these electrons and protons actually do get caught up in the magnetic domains of the Earth, and are accelerated down those force lines and come into the atmosphere, and depending upon the level that they are accelerated at, as you see here, there's kind of a sorter going on up here, that you have protons going to one side in the magnetic field and the electrons being brought to the other. One of the theories that I was reading recently is that the fact that the solar interplanetary magnetic field becoming stronger and weaker, moving across the force lines in the Earth's magnetosphere, create a certain amount of a kind of a generator working that causes particles to be pumped out of the sort of like a storage battery, and when those activities are great, more of the electrons move down in, and protons as well. Aurora actually are produced by both of them, but that gets involved. Let's just talk about the electrons. And essentially what happens there is you have a, what do I do with it? you have a this auroral ring around the polar regions here. That's what this is. This is day side, night side, and so on. And this is where you mostly see the aurora. That's why if you live in Ithaca, New York, you have certain percentage chance of seeing it. If you live in Daytona Beach, you might see it never, once in your lifetime. And if you live in Alaska or something, why, you know, you take it for granted, I suppose, because you see it quite a lot, as that ring is up in that particular area. This is just a ultraviolet photograph of the sun showing certain dark areas in the magnetic field in the chromosphere that producing, move along from there. Yes, this is something here that I pay particular notice to. This is a product of the modern age. This is satellite photographs of the auroral ring in the polar region, and it shows here this particular, again, the ring where these particles entering into the regions up there where the magnetic lines of force come around and allow those electrons to penetrate and cause exciting and relaxing reactions, giving us these light phenomena, various colors commensurate with the atomic responses of those gases. But giving a there's a number of these. So I show these specifically because early on in Birkeland's work, this was one of the first things that he observed. This is some more satellite photographs. Let's go through these. That you can see. That's Antarctica there, with the auroral ring taken from the satellite. This is okay. I often wonder how I make these particular slide arrangements. This is Birkeland's early laboratory, and if I can. And see if my own eyes can see it. I can't see it that well. Anyway, you can see his mercury vacuum pump. So, and here is his Crookes type discharge tube. Here is a generator. There are DC. There are certain. My glasses are not up to the task here of seeing all. There's some letters in there that I had noted that showed the various parts. But he had his vacuum pumps, his power supplies, which were, you can't see them here so much, were multi-disc static electric generating machines and induction coils of various size that he used. And here is the picture of his early discharge unit. You can see that the end down here. Actually, whoever lent me this laser pointer, thank you very much. That definitely makes things a lot easier. You can see the cathode or anode, depending upon what he was going to do in it. In this case, it's an anode. Here is a window down here with a kind of an O-ring, and that could be closed, and then you would pump the vacuum in it. And there's also several electrodes here, so you can do different. You can actually have this sphere here, which he called a terella, which had inside of it, this is a smaller one, but had an electromagnet, and he had different configurations of these magnets, and he created, you can begin to see the curious effects that occur here, with particle electrons leaving this terella, and you can see that with different magnetic workings here, there's a lot of phenomena that occur where the electrons are held in orbit around the sphere, and this resembles what I call a Crookes tube because it has kind of a pear shape to it, and you will see this afternoon when we talk about Crookes tubes that was a common shape to see. Very curious. I can tell there's just certain glow discharge phenomenon up here that this is the anode. You can tell by this anode glow that's available in it. Well, he proceeded, yes, here are the first series of his electron bombardment experiments in which the terella was used as the anode, the positive electrode in the experiment, and you can see that it is rather obvious, and so it was to Birkeland, that this auroral ring was being produced here along the polar regions for the magnetic domains, you know, the lines of force coming around and bringing these electrons available from the cathode at distance. So this, looking back at a few slides ago from the satellite photograph, Birkeland certainly, you know, had the right idea, and his experiments proved, at least in this particular case, that this was a working hypothesis. Here's some more of the same. There's many photographs available. It is, I have to throw in here And when you live around a great university, or if you work for them and so on, a lot of times you, your opinion can kind of be a love-hate opinion. Things happen one way, things happen in another way. But I must say that that Cornell University has a wealth of books and experimental stuff and equipment and the loading docks for, I have a small organization called Midnight Electronics. That doesn't indicate that we go around and do things illegal, but most of the building managers always say, look, get this out of here, this is great, you know, but come back at midnight because none of the professors are out. They see it taken out, they want us to keep it for another 20 years and we don't need it. So they have a tremendous resources. So I was able actually to get Birkeland's original work on this and make the slides. Let's move on here. Some more of the same kind of phenomenon here. Different effects from magnetic changes and changes in the actual way that the terrella was moved in the field of electrons from the cathode. That would be what do you call that? It doesn't matter. And here's some more. Again, these are really quite spectacular, seeing these various effects and looking at what you would consider to be the night side and the day side auroral phenomena and how the effects of particles striking the terrella would have been made. And he now his vacuums that he used on this, he used a number of vacuums, and they were in the range of about from 1 micron of vacuum up to as high as about 1 torr. And he varied all these things to see what kind of effects he could have. Actually, those of you that have ever seen gas X-ray tubes in operation know that the focus cathode in a gas X-ray tube is going to be very finicky. If the vacuum gets too low, then the focus recedes, and if the vacuum gets too high, the focus extends, so you don't get an exact focus on the target of the tube. And in the early days, they had to put regulators in X-ray tubes so that you could keep a midline and take a good picture without losing your focus from the cathode. He experienced this and actually wrote a considerable amount about that effect here. Here's some more of the same. You can see the wires, that's upside down, but it's okay. You can see the wires extending into the terrella. And he used, actually, there's some very interesting figures about the amount of magnetizing current that he used. He used up to as much as 50 amperes at as much as, how much did he use? 80 volts, 100 volts. The amount of the magnetic field, actually he gave some figures in Teslas, which I thought was actually nice to see. Actually, not him, but later on analysis of his work used that. It was some, I don't remember, it was a considerable amount, varying that. And his voltage that he applied to these tubes, depending on the vacuum, could go from about as low as 600 volts up to about 22,000 volts. He had some pretty amazing equipment to do this. And here we go with a few more slides. All of these in the paper, in the book, go into a lot of details about what he was actually up to. Of course, like any good Tesla coil builder or hot rod or anybody, you know, the 6-cylinder engine not quite enough, so you have to try something larger, and you might be working with 0.01 microfarad. That doesn't quite give you what you want. You have to move up, and gradually so did Birkeland. And here is an example of a box that he built, and this particular box, my cheat sheet here, the size of it is 36 by 36 by 55 centimeters. And here, the vacuum he's working with here is 0.01 millimeters of mercury. And this it just shows the larger structure that he wanted to work with, and demonstrating here quite clearly. You can see the process here, obviously, from the effects here, just what I talked about a little earlier with the phenomenon of the vacuum discharge tube. Here is the Crookes dark space here, and this is the cathode glow. And I think if you really looked up close, you can see the Ashton dark space in here, and here's the negative glow. And then here's the Faraday dark space up here, and then you begin to approach. You don't see all that. There isn't a positive column in here. The structure doesn't, I guess, lend to that. But again, you can see the electrons are obviously brought around and into the magnetic lines of force, striking what would be, in this case, the polar region of the magnet, creating the auroral zone there. So he, we have, oh yes, here's the next phase. We have the same thing again here. Now this time what he did was to get into a really, even a more advanced thing with this. This whole operation over here is covered with phosphorescent material. What did you say that was? I believe that we're looking at some form of barium platinocyanide, which, by the way, was the early X-ray screen material that was used to observe X-rays. Recently, I find out that you can't get those anymore. So I feel that I have a fair collection of them. It's something that, you know, comes along. Anyway, they don't make them anymore. And Birkeland did this so that you could see. He built a number of well, we can move on and see that. Time is getting short. Here we go. He used all kinds of different pegs and effects in here, different magnetic, different attitudes, even different vacuums to show different places where shadows were created. Again, looking at many different ways of observing the electron bombardment of these targets in line of trying to understand the particular effects that would take place in the atmosphere. And these are very curious. There's a number of these we can look at. Here's some more. Strange looking and many effects. There's a window in that following, I guess, off of some of the Crookes magnetic effect tubes, or you get a window, see the beam striking the I guess these, I want to have these here. This is back again to the a few other experiments with the earlier tube. Have a look at that. Some more magnetic effects. Now, moving right along here, of course, Birkeland began to stop and take a look at this and say, you know, some of these effects that are taking place, he wondered if comets and comet tails and Saturnian rings and other phenomenon that observed by astronomers couldn't be explained by this particular effect, these particular effects. And in 1901, he actually decided that maybe the rings of Saturn, for instance, and we'll move along to see some other things, could be, yeah, here's some very curious effects here. Couldn't be the fact that there was some kind of a magnetic arrangement generated by the planet that was actually holding aggregate particles together in different rings around the planet, which I believe is the current reality of that. Those little sort of things that, you know. And so he made a lot of experiments using, in this particular case, using the Terrella as a cathode, so that the electrons that coming out of it, the different effects could be seen, and he could vary his parameters and get these different effects. In the upper right-hand corner is, I don't know why they shoved it in here, but it's a marvelous photograph of an eclipse in 1901. Yeah, an eclipse in May 17th, 1901, in which shows, and he went into some explanation about the idea of the magnetic domains, the interplanetary magnetic forces displayed here during the total eclipse. You can see these effects are rather interesting. These were some experiments he was doing with comet tails, trying to understand, you know, what the actual composition of comets were, and he thought that maybe there was some kind of well, this was the carbon experiment, and he used carborundum and charcoal and so on, and when it was, you can see actually when it was bombarded in the anode, you got all kinds of interesting effects. It reminds us perhaps of carbon button lamp. Here's some of the positive column effects and so on. This goes into great detail, and I don't have the time to really get too carried away with this. In talking about comet tails and so on, this is he used J.J. Thomson's earlier experiment with what is this? The Lorentz force. When an electron encounters an electrical field, it can be pushed off at right angles to it. And I think Birkeland's idea here was that this particular idea here, these particles this looks like the head of a particular comet that he had looked at and began to experiment with that. Let's see. This is another thing that a discharge tube, this was his own drawing, looking at, now here's the cathode here, the anode is over here. These are both cathodes again. This particular one is connected to the negative pole, and this one is just grounded. And he's trying to explain the idea that the electrons coming, or the corpuscles, he calls them, coming from the sun, striking where a comet is coming in with the charge repulsion effects here would give you this idea of a comet tail. And although we know that the solar wind reaction with the I guess the ice particles of a comet and the ultraviolet spectrum reaction with that causes melting of that, and you get a tail effects. This was Birkeland's original just explanation of how it might work in terms of charge repulsion and some magnetic effects. And here's the comet that he what he studied and liked as an example of this Donetti's comet of 1858, which has a great photograph of that, trying to explain some of these effects of the comet tail. There's another great one there, and that's varying the magnetic field and the voltage that is present on the. In this case, the Terrella is negative, and giving off electrons, showing how, as he claimed, that the Saturnian rings might be held in place by a particular effect of the magnetic domains of the planet versus the particles that. Or that field emanating and particles being held in place by it. Here's some more very curious effects again with the Saturnian ring idea. And this over here is something you'll see as we get to the last of the photographs. He started using capacitors and having pulse effects with his experiments, and he began to get these particular, he called them pencil holes, where pencil rays would shoot out from these particular things with a disruptive discharge effects put on the Terrella. And we can see some more of these. Yes, there's some more. We're running out of time here, but I swore that this year Michael was not going to come up and tap on his watch when I was just getting my stride, and it's going to work out, I promise you. I have Lowell's watch right here, and I think I have 4 minutes to finish, and I will do it. This again is another disruptive discharge being pulsed through that, and you can see again this is the Terrella being the cathode, and these pencil rays emanating out from it. Curious effects. Here is Birkeland himself. You can see he's even moving into. No, this is the same size stand that he has, and here's Birkeland himself at the controls. Over here, I think, is his capacitor bank. And what else is around here? I think you can see some mercury Sprengel type pumps and so on in the laboratory. Some more experiments of that Saturnian ring nature. Let's see. This is rather beautiful. Again, this was an arrangement of. This is a complicated one. This pulses, high current pulses, and with the dipolar magnetic field in this case where you're getting this obvious effect of but in this case, instead of the particles actually emanating from the Terrella itself, you can see that the metal plates on the floor and above are where the actual pencil rays are emanating from, and then they, as it was shown earlier, produce that auroral ring effect and strike against the Terrella. Another kind of what he called the nebular effect, how nebulas might be formed and so on. Here's now this is the larger Terrella sphere in the larger case with thicker glass, and they had some accidents with this to keep building thicker experimental equipment here. And this is Birkeland on the left, and Olaf Davik, his assistant, on the right. Again, actually this looks like some kind of amazing a Tesla coil capacitor bank of sorts, which I don't know. That's a real beautiful one there. This is where the Terrella is the cathode. See the magnetic domain there. It's quite nice. It's interesting to see these laboratories. They all kind of have that turn of the century, that same kind of wooden look to them. All the kind of, when one of these on the fringe flaky characters, they shove them out in the back somewhere to some sort of a unused barn or whatever. I believe the Curies had the worst possible kind of place to work to make one of the greatest experiments. Perhaps there's something to that, you know, some kind of posh, nice place to work doesn't produce the effects that might be produced when you're freezing your rear end off, and you know, and there's, you know, problems all over the place, you know. So. And this is the changing the same experiment, changing the polarity around again, where the Tarella is the anode in this particular case. You can see the discharge phenomenon in the tube. I'd love to have seen this equipment up close. It must have been one heck of a thing to look at. 11 o'clock on the nose. How about that? I've made it within the time frame. Thank you very much, and field some questions if you'd like.